there's several special random variables that come up often enough that they have special names, and one of them is the binomial random variable. Typically, a binomial random variable involves, well, the prefix bi means two. So uh, typically, you have a population uh, with that has either one of two characteristics. Either they get flu or they don't get flu, or maybe either they favor Biden or they don't favor Biden. And you have a sample from that population, and X represents the number of individuals from that sample that have the particular characteristic in question. So that would be a typical binomial random variable. In this case, we have a flu epidemic. 30% of children get the flu, and a random sample of 10 children want the probability that 4 get the flu. And so we did this example before, except we didn't call it binomial. But it is binomial because each person in the sample either gets the flu or they don't get the flu, and they have a set probability for each of those. So what we did before, we had a sample path where 4 got the flu and the other ones did not. And so the probability of that sample path, if you have 4 getting the flu and 7 not, the probability they get the flu is 0.3. 1 minus 0.3 is 0.7, so the probability they don't get the flu is 0.7. So you have 0.3 times 0.3 times 0.3 times 0.3 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7, or you can shorten that 0.3 to the 4th power times 0.7 to the 6th power, 0.000952,957. And the number of paths where 4 get the flu, 10 choose 4, which came out to be, when we did this before, it came out to be 210. So the probability that exactly 4 get the of the 10 get the flu, you multiply the number of paths by the probability for each path, you get 0.2001200942. So anyway, so this is an example of binomial. More formally, we're going to let X represent the number of children in a sample who get the flu. X is approximately binomial with n equal 10 children, and the probability of flu p equal 0.3. So, and the probability of no flu is 1 minus 0.3, which is 0.7. So notation, X is a squiggly sign, X is distributed B binomial 10 comma 0.3. So this notation sort of describes the binomial. For binomial, that's as much as you need to know in order to compute the probabilities. You need to know sample size, and you need to know p. Once you know p, you can compute you can compute q, which is 1 minus p. For X to be a true binomial, the sample would have to be from an infinite population. So typically you have a sample of a couple hundred or a couple thousand from a population of millions. So it's a sample of a 1,000 people from a population of millions. That's not an infinite population, but it's big enough that the probabilities are close to being binomial, and we usually treat that as a binomial. Generally, the binomial random variable represents the number of people or things with a particular characteristic in a random sample of size n. It's a proportion with that characteristic in larger populations p, and the proportion without that characteristic q, 1 minus p. So the formulas for the binomial, probability x equal little x, n choose x, p to the x, q to the n minus x. The mean of binomial is n times p. Standard deviation, square root of npq. And we can use that to compute probability. So the probability that 2 get the flu is going to be in this example here, n was 10 and p was 0.3. So this is going to be 10 choose 2. 0.3 to the 2, and 0.7, 10 minus 2 is 8. So we could put that in the calculator. It's 10, the PRB, right arrow, 2 equals times 0.3 exponent 2 times 0.7 exponent 8 equals. And that should do it. 10 PRB, right arrow, 2 equals, and then times 0.3 exponent 2 times 0.7 exponent 8 equals 0.233. We get 0.2334744, and a long string of decimals. Okay, so probability of well, okay, so the mean, so that's probability x equal 2. The mean is n times p, so that's going to be 10 times 0.3. So on the average, we would expect 3 children to get the flu. Standard deviation, square root of n times p times q. So it's second square root 10 times 0.3 times 0.7. We get 1.449. 37675 children. Okay. Okay, so here's another example of binomial. This one is actually a true binomial because okay, so yeah, because this is a true binomial because there's no whether Sandy gets one question right is not going to be affect whether she gets the second question right. So this is the other one was approximately binomial because we have a sample from a large finite population, and the probabilities change slightly once you pick somebody from the population. The probabilities will change slightly for the second person, but for a multiple choice test, but Sandy's answer to 1 is not going to affect her her chances of getting the next question right. So Sandy's taken a multiple choice test with 7 questions. Each has 5 choices. So if Sandy is just guessing, then on each question Sandy has a p equal 1 out of 5 or 0.2 chance of getting the question right, and a q 4 out of 5 or 0.8 chance of getting the question wrong. And we want to know what is the probability that Sandy gets at least 70% passing. So 70% as a decimal is 0.7. There's 7 questions altogether. 0.7 times 7 is 4.9. So Sandy needs to get at least 4.9 questions right. But we're just going to assume there's no partial credit here. So she's not going to get 4.9 questions right. Either she's going to get 4 right, or she's going to get 5 right, or some other number right, but she's not going to get 4.9 right. So in order to pass, if she gets 4 right, she's not going to pass. If she gets 5 right, she will pass. He or she will pass. So Sandy needs to get at least 5 right. So we want to add the probability x equals 5 plus the probability x equals 6 plus the probability x equals 7. So if we plug into the formula, this is 7 choose 5, 0.2 to the 5, 0.8 to the 2, and multiply those out. Get 0.0043 something, and then 7 choose 6, 0.2 to the 6, 0.8 to the 1. This is the probability Sandy gets 6 right and 1 wrong. This is the probability that Sandy gets all 7 right, 0.2 to the 7, 0.8 to the 0. And if we add these up, we get 0.004672. So this is a pretty low probability. It's not likely that Sandy will pass by guessing. How many questions can Sandy expect to get right by guessing? So that's going to be the expected value is n times p. So we have 7 questions, and p is 0.2. So on the average, we expect Sandy to get 1.4 questions right. Standard deviation, square root of sigma square root npq, square root of 7 times 0.2 times 0.8. Second square root 7 times 0.2 times 0.8. So I get 1.05. So on symbols, x is distributed b parentheses 7 comma 0.2, but this x is binomial with n equals 7 and p equal 0.2. Okay, so there's a random variable that's related to the binomial random variable, and it shows up a couple of times in some of the exercises, but it's a geometric random variable. So again, Sandy has taken a multiple choice test, but this time the number of questions is unlimited. The test is not finished until Sandy gets a question right. Each question has 5 choices. Thus, if Sandy is just guessing on each question, Sandy has p equal 1 out of 5, or 0.2 chance of getting a question right. Q equal 4 out of 5 equal 0.8 chance of getting a question wrong. What is the probability the first question Sandy gets right is the 8th question? If you think about the tree, this would be a single path from the tree. It'd be wrong, 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 right. That's just one single path from the tree. So it's 0.8 times 0.8 times 0.8 times 0.8 times 0.8, 0.8 times 0.8 times 0.2, 0.04 something. So, Sandy has a 0.8 chance of getting it wrong. So we have 7 wrongs. That's 0.8 to the 7th power, and then 1 right. So it's times a 0.2. So that'd be 0.04 something. Probability that Sandy gets the first question Sandy gets right is the 7th question. Well, we have 6 wrong followed by a right. So we have 0.8 to the 6th power times 0.2, which is 0.05 something. So this is a geometric random variable. It's related to the binomial, except there's no sample size. There's no n. There's no limit on the number of questions. The question is not finished until Sandy gets a question right. You can use the notation G parentheses n comma p. Oh, oops, why do I have an n there? no, it should be just a P. GP. Because there's no sample size here. It's you can take the same values as a binomial. You can even use the same tree, but the tree is indeterminate size because we don't have a sample size, and we only need one path from the tree. And there's also a formula for geometric probabilities. Probability x equals little x, p times 1 minus p to the x minus 1. So this is the 0.8 to the 7th power. This is the 0.2, right, for the part A. Okay, so okay, here's a similar question here. This is it's like the geometric, but it's a little bit different. Again, Sandy is taking a multiple choice test, and this time there is a fixed number of questions. There's n equals 7 questions. Each has 5 choices. So this is like the binomial. Sandy is just guessing that on each question, Sandy has a p equal 1 out of 5 or 0.2 chance of getting a question right, and q equal 4 out of 5 or 0.8 chance of getting a question wrong. Probability that the first question Sandy gets right is the 8th question. It's 0 because there's only 7 questions, right? Probability Sandy gets first question Sandy gets right is the 7th question. This will be a single path from the tree. That means 6 wrongs followed by 1 right. So it's 0.8 times 0.8 times 0.8 times 0.8, etc. times 0.2, 0.05 something. The 6th question, that'd be 5 wrongs followed by a right. It's going to be 0.06 something. The 5th question would be 4 wrongs followed by a right, 0.08 something. The first question, that would be a single path, 0.2. For one thing to note here is that this is the highest x can go is 7 because the sample size here is 7. But for x equal 1, 2, 3, 4, 5, 6, or 7, the probabilities are the same as for the geometric probability. The only probabilities that are going to be different are the probabilities for anything above 7, because the sample Sandy is going to stop after 7 questions no matter what for this test here. This test only has 7 questions. So for values of x, for 1 through 7, it's the same probabilities as the geometric probability, and for the higher probabilities, it's just going to be probability 0. It's no longer the same as geometric. So it's a similar to the geometric. With either these, I think it's maybe just as easy to use the single path from a tree as to use the formula. You can use the same for both the geometric and this one here. They're both binomials, and there's maybe a couple of problems in the assignments that use these geometric or semi-geometric probabilities. And that concludes this presentation.